So go ahead.
Thank you very much, Samuel. Good afternoon or good evening, everyone, or good morning, depending where you are. It's a pleasure to present our work on spatially modulated phases of superfluid helium-3 in this webinar. So this is a collaboration between group at Royal Holloway and Cornell University. This picture shows in a cartoon way the essence of what we're looking for. We're looking for helium-3 under confinement. So there are two walls that restrict the space where helium-3 is, and the distance between them is comparable to the size of the Cooper pairs. And there is a prediction and possibly observation that something periodically is more, some superfluid properties periodically modulated along the slab, breaking the translational symmetry. So I have a brief introduction about other types of Cooper pair density waves. The first one to be predicted, and also with some evidence for experimental observation, is the full deferral Larkin of Chinnikov state in superconductors, which where pairing between two electrons with different momenta helps avoid Pauli pair breaking at high fields. What's interesting is that originally a one-dimensional modulation of the order parameter has been considered, but more recently people have looked into two-dimensional patterns, and this is what this talk is about. Then something quite different is a prediction that aims to explain pairing in high TC Cooper rates, where by trying to pair electrons which are on the same side of the Fermi surface, you might induce pairing between them just by ampere force because they are moving in the same direction. There is a multitude of pair density waves intertwined with other orders such as charge or spin density waves reported recently, and this is a review of such orders. Under confinement, spontaneous modulation of the superfluid order has been predicted for D-wave and P-wave systems for the superconductors and for helium-3, both in films and channels. And this is the type of pair density wave relevant to this talk. This is a phase diagram under confinement to three different thicknesses observed at Royal Holloway. And there is evidence that in the thickest of the slabs, just below the A-B transition, so A and B are two superfluid phases of helium-3. This is the bulk phase diagram, and we're looking at low pressures, limited by bowing of the non-fluid cavities that we use. And there is a significant alteration to where the A and the B phases are on the phase diagram due to confinement. And there is evidence that within the B phase, just below the A-B transition, inhomogeneous, spatially modulated state takes place. We also know that in a thinner slab but at higher pressure, slightly further away from the A-B transition, the Nmr signatures we observe are consistent with there being no such modulation. Here is a brief introduction into the superfluid helium-3. It's a strongly correlated Fermi liquid in which Cooper pairing is in a P-wave channel, with which means orbital Cooper pairs have orbital and momentum and spin equal to 1, and that means that we can have a non-component complex order parameter and multiple superfluid phases. In the bulk, as I've shown on the previous slide, there are two such phases: chiral A phase and time reverse invariant B phase. A phase has very anisotropic properties, whereas B phase, which is composed of all three components of orbital and spin triplets, is quasi-isotropic. Different techniques allow to stabilize other superfluid phases, and that includes magnetic field, anisotropic aerogel, and confinement. In addition to the superfluid phase, the P-wave order parameter has other degrees of freedom, and the pairing energy is invariant under separate rotations of all the pairs in orbital and spin space. The orbital momenta of the pairs can be controlled by boundaries and flow, and then spin couples to magnetic field, and then spin and orbital momenta coupled together by very weak dipole interaction. So here I will show an example of how we can manipulate the order parameter of the B phase. We start with the B phase I've shown on the previous slide, where we have 3 components of the orbital triplet, and then we rotate the spins about the z-axis. So that gives, that gives the phase prefactor to the components which have non-zero projection of S on the axis of rotation. And if we rotate by an angle of pi, then we get a state where the sign of these 2 components is different to the middle one, which did not change. And then by adjusting the overall phase, we get to a state where the LZ equals 0, Z equals 0 component changed sign. One can get from a state with a positive and negative amplitude of this order parameter through that continuous transformation, but it's also possible to have a domain wall where nothing else changes, where this amplitude changes sign going through 0. And such domain walls have been considered in the bulk, and there is evidence for such domains being observed as metastable defects in the bulk and in aerogel experiments. And under confinement, such domain walls are predicted to have negative surface tension and therefore proliferate. So the effect of confinement on superfluid order parameter is in suppression of the components of the order parameter near the walls. And this suppression is anisotropic. The components with orbital momentum perpendicular to the wall are fully suppressed, whereas the other components are either unsuppressed at all or suppressed but less than the other ones, depending on the nature of quasi-particle scattering at the surfaces. And here we are talking about whether that scattering is diffuse or specular or something in between, with finite probability of specular scattering. So in this work, I will be talking about 2 situations which can be stabilized in the same experiment by adding different amounts of helium-4 to our system. So helium-4 goes on the walls and either forms the solid or forms the solid covered by a thin layer of superfluid. And this changes the nature of scattering. If you fill the cell with pure helium-3, something else is going on, and I invite you to read this recent paper which discusses this in detail. Now, if we look at the A phase near the wall, then confinement or surface pair breaking in general have the orientational effect. So here is A phase with the orbital momentum of the pairs perpendicular to the wall, here parallel. So confinement will rule out that orientation over this. In the B phase, because all components of the orbital triplet are present, such an orientational effect doesn't take place, and instead the B phase develops a distortion where the amplitude of these pairs goes down. And in a slab between 2 parallel walls, amplitudes of both components develop spatial variation. No spatial variation for the A phase for specular walls, but spatial variation for all components of the B phase in all situations, and also for the A phase for diffuse scattering. Now, under confinement, presence of the domain wall that I showed earlier is predicted to reduce surface pair breaking for quasi-particle trajectories that cross the domain wall, where the sign change due to the scattering is compensated by the sign change due to the going into the different orbital parameter state. And there's a prediction that such domain walls spontaneously nucleate in the B phase in the slab, and a plane pair density wave has been predicted. It's found that its modulation, its wave vector is of order of pi over the thickness of the slab. So the size of the domains is close to the width of the slab. And at the domain walls, additional components or the order parameter emerge. And within Ginzburg-Landau picture of energy caused by spatial gradients of the order parameter components, stability of the stripe phase is the result of that simultaneous spatial modulation of different components of the order parameter along different axes can lower the gradient temperature. So now back to phase diagram. Here is phase diagram with diffuse walls, in which we show that in very thin slab, we suppress superfluid transition, and then there is a phase below that, and nothing else. And then as we increase the slab thickness, we reduce the suppression of superfluid transition, and we allow for the B phase to stabilize. If we change the boundary condition to specular, then we eliminate the suppression of A phase superfluid transition, and we slightly shift the AB transition up in down in temperature. And we can find that all these three phase diagrams are quite universal if we plot ratio between the thickness of the slab and the coherence length, which is a function of temperature and pressure. So at bulk superfluid transition temperature, coherence length diverges, and then going up in these coordinates is equivalent to going down in temperature. And there is a universal value of d over psi where the superfluid transition occurs. And then at the higher value of d over psi, the B phase is able to stabilize. And whether certain phases can or cannot be observed in a given slab is determined by the range of d over psi that is limited by the slab thickness. So here I plot that range for the three thicknesses we've used. And then this is the range in these two coordinates, in PT and in d over psi versus P, where the stripe phase, where we observe evidence for a pair density wave. Now I will say a few words about experimental techniques. So we fabricate a cavity out of silicon and glass, or more recently, fully out of silicon. There is a well-defined slab etched into silicon, and then a glass wafer is bonded on top of that. There is a hole drilled through silicon, and we can attach a fill line and connect this slab to a heat exchanger with a large area of silver powder. So we can cool down helium in the heat exchanger, and then that cools down helium in the slab. What's important is that at zero pressure of the liquid, this cavity can be made very, very uniform at a nanometer level. But under pressure, we observe bowing, and that plays an important role in some of our observations, and also limits the pressure range where we did most measurements, because we don't want to study effects of confinement where the cell is a balloon. We use ultra-sensitive NMR spectrometer based on a two-stage DC squid in order to detect signals from small numbers of spins. Our spectrometer is tuned at 1 megahertz, so we do NMR in the field of 300 Gauss that's oriented perpendicular to the slab. In more recent experiments, which I described in this paper published this year, we have included a bulk volume, separated from the heat exchanger by the slab, and we are now able to have a very accurate thermal model that tells us that there is negligible temperature gradient across the slab, and also we can correct for small temperature gradients between helium in our cell and the heat exchanger, which temperature we measure directly. This is Nmr signatures, so we do NMR, and because nuclear spins have degrees of freedom of the Cooper pairs, there is a shift to the frequency at which NMR precession is observed away from normal frequency, which is proportional to the square of the energy gap. So this is an observation of a second order normal to A phase transition, followed by a first order transition into the B phase. And in the B phase, we observe two states that nucleate stochastically. So we cool down, and sometimes we end up in this state, warm up, cool down again, end up in the other state, or in this state again. Here I use a musical notation sharp and flat to describe the sign of the frequency shift, but not its size. And it's important that these two states in the B phase are not states with positive and negative amplitude of the Lz=0 component. Instead, they're different spin orbit states. So in order to go from B sharp to B flat, we need to rotate the spins of all the Cooper pairs. The order parameter in our system isn't homogeneous. For a start, it is a function of coordinate across the slab, but we're looking for variation along the slab as well. In the A phase, this is easy to deal with. So the variation is happening on a length scale of slab thickness, D, which is much smaller than the dipole length psi D, which is 10 microns. Under these conditions, the NMR precession in this inhomogeneous system is homogeneous, and the frequency shift is determined by the average squared energy gap. And this paper, which I referred to several times already, and this is a figure from it, can use this simple relationship to precisely measure energy gap and compare it with quasi-classical theory for different boundary conditions. In the B phase, the situation is more complicated because there are two components of the order parameter, and there are three quadratic combinations that we can build. And this paper describes quite long equations that relate the frequency shift to these dimensionless combinations of the quadratic averages that we measure. We chose those quantities because, I'm sorry, there should be a square root sign here. Because for uniform order parameter, both of them are equal to just the ratio of delta perpendicular delta power delta. So as we have just discussed, we developed a technique for modeling NMR when the order parameter changes across the slab. So if the variation along the slab is also on a length scale that's smaller than coherent dipole length, then exactly the same techniques apply. Unfortunately, for the stripe phase, the period of the size of the domains is predicted to be only slightly larger than slab thickness, which in our case is also within this regime. So we measure small q and large q in 1 micron slab at 0 pressure. And what we observe is that while large q, First, what we observe is the small q is not equal to 0, which would be the signature of the stripe phase. So this is easy to see. In the stripe phase, delta perpendicular spends the same amount of time positive and negative within the slab. So it averages to 0. We don't observe this. So under the conditions of our experiment, there is no stripe phase. However, we can also do a quantitative comparison of these numbers, of these quantities, to the predictions of quasi-classical theory for a slab without domains. And we find that the large q is in agreement with the theory, while the small q is reduced. And we interpret this as a situation where domains are present, but the amount of domains where delta perpendicular is positive and negative are unequal. And we can build a simple model in which we relate the ratio of small q to large q to the amount of domains, to the imbalance of domain A. And we plot that here. And what we observe is just below the AB transition, where, the imbalance of domains is consistent with a ratio of 1 to 4, which is what one would expect for a system of circular domains, polka dots, where the size of domains and the distance between them are similar to the pitch of the stripe phase. We need to be careful and consider whether the observation of inhomogeneous order parameter is related to metastable effect. And what we observe, or the way we do our measurements, is we cool down and then we do NMR while slowly warming up the system. And we observe that the small q is dropping below the theory as we warm up. So this is consistent with domain walls developing within the system rather than being relics of disorder or quenched at the cool down into defects. So the question is, are dots intrinsically stable in comparison to the stripe face? And I hope we will hear about it in the next talk. And then experimentally, we also need to remember that to create stripes, one need to change the sign of delta perpendicular in a macroscopic part of the experimental cell along the entire stripe, whereas the dot is microscopic in all dimensions. Therefore, it's possible that the nucleation barrier for formation of dots is lower. And this could be the reason why experimentally we observe stripes, we observe dots rather than stripes, even if stripes are energetically more favorable. And then it's important to acknowledge that in this experiment, pinning of the main walls was possible and might play a role in some of the observations and prevent the formation of the uniform stripe face. And then it would also result in a disordered system, perhaps of dots, based on the ratio of small change and large change. So the reason we know about pinning is that we observe hysteresis between the A-B transition on cooling and on warming in our NMR experiments. So here I'm presenting such observation in the 0.7 micron slab at high pressure. And this is attributed to scratches on the surfaces, on the glass surface of the cavity. Subsequently, a technique was developed by Nikolai Zhelev and his colleagues in Cornell to polish these scratches away. And a cell without scratches was used in a torsional oscillator experiment with 1 micron cavity. And in this experiment, what is observed, so this is a superfluid fraction sensitive to the A-B transition, there is width to the transition similar to the NMR experiment caused by the bowing of the cavity under pressure. And there is supercooling of the A phase, but once the B phase is nucleated, you can go back and forth along this line, so there is no hysteresis anymore. So the conclusions we draw from this is that in the NMR experiment, including the 1 micron experiment I just described, pinning of the domain walls is possible, but also we observed that both of these experiments, not the 1 micron slab at 0 pressure, but all of these experiments at elevated pressure have slab thicker in the middle than along the peripheries and near the field line. Therefore, there is intrinsic nucleation of the B phase in the slab. And as you can see here, and also here, the supercooling of the A phase is very small. And we find that this is a systematic behavior that in 0.7 and 1.1 micron slabs, supercooling is less than 30, 50 microns. And we have a byproduct of one of our recent experiments in which there is a 10 by 50 micron trench used as a far-end bulk marker, where that volume is separated from the rest of the world by the A phase in a roughly 100 nanometer slab. And in that experiment, we did observe much larger supercooling for up to 5 days, and B phase nucleation was not triggered by liquid helium transfers. In the rest of my talk, I will compare this observation consistent with formation of pair density wave with a 2-dimensional nature in our experiment with theoretical predictions of where pair density waves might be stable. So again, I'm plotting the 2 phase diagrams in the experimental coordinates of temperature and pressure, and they collapse both of them onto these coordinates of pressure and reduced thickness. So first, I compare the experimentally observed AD transition to the AD transition predicted by the BCS theory, not considering spatial modulation. So we observe that the A phase is much more stable at low pressures than predicted by the BCS theory. So this is a result of strong coupling effects, which stabilize A phase in the bulk at high pressure. And this shows that they extend down to lowest pressures. Then within the same BCS theory, stripe phase are predicted to be stable around the AB transition, extending a little bit into the A phase and much more into the B phase. And everywhere where the stripes are stable within the weak coupling theory, within the BCS theory, we observe the A phase. And then there is a work by Joshua Wyman and Jim Soules, in which Ginzburg-Landau theory has been extended to low temperatures by giving the beta parameters a temperature dependence. It shows now that the AB transition has a pressure dependence in this reduced thickness, qualitatively similar to what we observed experimentally. Their AB transition doesn't match ours. And then there is also a very small region of where the stripe phase might be stable, which is close to where we observe the AB transition, but it's not clear whether theoretically the stripes are stable in this region or not. Then there is recent work which I didn't add to this graph. So here are the numbers. This work from Alberta considers a two-dimensional modulation, polka dot phase, and they find that it's stable very close to the original AB transition. So this is Ginzburg-Landau theory, but using beta parameters from BCS theory, so there's no pressure dependence to that prediction. So the conclusion is that existing theories underestimate strong coupling effects at low pressure because they don't reproduce the AB line that we observe, and that the stability of domains under confinement is an open question. So experimentally, we have evidence for spatially modulated state here at zero pressure. And we know that at this point, as observed in the 0.7 micron slab, there is no evidence for domains. So here, tentatively, I show a triangle of the spatially modulated phase. It could also be a band extending along the AB transition, but that would not qualitatively agree with the prediction of the AB. Prediction of the Ginzburg-Landau theory. And then the last thing I wanted to say is that prediction of the stability of the spatially modulated phases under confinement is a very difficult problem for the existing theorists, I believe. I hope that the theorists will not give up and will develop more and more quantitatively accurate tools. And so here I'm showing that the well-developed BCS and Ginzburg-Landau theories fail to describe such a fundamental property of the bulk helium 3 as the AB transition. So in the BCS theory, B phase is stable everywhere, and then within the traditional Ginzburg-Landau theory, there is a polycritical point, and above polycritical pressure, A phase is stable. So Jim Soules and his co-workers were able to model this phase boundary very well by giving beta parameters a temperature dependence. I'm sorry. And then this temperature dependence, the strong coupling effects vanish exactly at zero temperature. And here is some recent work from our lab of measuring the A phase energy gap in a thin slab, but with specular walls where the A phase is not suppressed. And here we compare at each pressure our experimentally measured energy gap to the prediction of the weak coupling theory, dotted line, trivial strong coupling, where the heat capacity jump at TC is used to rescale the gap. And so what we see is that the temperature dependence of the energy gap observed experimentally is weaker than within trivial strong coupling. So qualitatively, it's in agreement with this model. But we don't see the energy gap dropping all the way to the weak coupling value. So the theory needs to develop a more realistic temperature dependence of the strong coupling effect. And similar results have been observed in the A phase stabilized by high magnetic field by Douglas Osheroff and his colleagues. With this, I would like to acknowledge a long list of collaborators, both experimental and theoretical, of this work, and the funding from EPSRC, European Microcarbon Platform, and National Science Foundation. And I would like to draw my conclusion and thank you for your attention. And I will be very happy to answer your questions.
Thank you, Lev. This is very interesting. Do we have any questions? Jim Solz has a comment, please.
Very nice, Lev. Thank you. Regarding extending the strong coupling GL theory to zero temperature, we didn't imagine that the GL theory should be extended down to zero temperature. We were trying to capture the AB transition and extension down to 0.5 TC or so. So we were quite aware that the scaling produced weak coupling at zero temperature, but just to let you know, we didn't want to extend it to zero temperature. But we do have, as you may know, there'll be hopefully results in the near future on a full strong coupling theory that does extend to zero temperature.
So I'm really looking forward to seeing the results of that theory, and perhaps we can compare it directly to this experiment.
Yes, indeed.
Thank you, Jim.
All right, thank you very much. I do have a couple of things I would perhaps like to ask Lev, but maybe we will move on at this point unless there are some other questions that people want to ask right now. Well, I'm not seeing any at least. So let us assume we can postpone these details I want to ask and other debate to a later time. And I'll thank Lev for this very nice talk. And let's move on to the next one.
Thank you.
All right, we can see your slides and I think also your mouse, so everything works. You can start.
Okay, thank you. First of all, thank you for giving me opportunity to talk our recent work here. So today I'm going to talk about the spatial modulated superfluid phases in confined helium-3 from the theoretical side. So actually, the main player of this work are Takeshi, who is my student, and Takuto Kawakami, who is my long-term collaborator. And so I'm going to talk about the pair density wave, PDWs. So PDW have been widely discussed in the context of superconductors. And according to the recent review paper by Daniel Arterberg, the PDW is a superconducting state in which all the parameters oscillate periodically as a function of a real coordinate, and the spatial average of all the parameters vanish. This is the definition of PDW. And the typical example is, as Lev already told us, the FFRO state, which is a superconducting state coexisting with the paramagnetic moment, because the Cooper pair has a finite center of mass momentum, and the paramagnetic moment can be accumulated in the nodal plane. And another example is a superconducting stripe state, which has been discussed in high TC cuprates. And for instance, LBCO is a superconducting state, which is accompanied by the charge density wave and the spin density wave above TC. And owing to such a spatial modulation of competing order, the resulting superconducting order parameter has a spatial oscillation in atomic scale. This is another example of the PDW in the strong coupling limit. And anyway, in superconducting material, the PDW state can be stabilized by applying time reversal symmetry breaking field or the interplay with competing orders. And the study of PDW state in superfluid helium-3 was initiated by Nmr Signatures and Jim Solz, and who discovered the existence of the new phase, which is now so-called stripe phase. And in the stripe phase, one of the order parameters, the AZZ component, has a spatial modulation along the surface, surface. But of course, the spatial modulation of order parameter costs the kinetic energy. But usually, this energy cost can be compensated by the condensation energy of induced off-diagonal component, say AZX, because AZX component is insensitive to the surface boundary condition and can survive even in the surface region. So this induced component can gain the more condensation energy than diagonal component in the vicinity of the surface. So anyway, the stripe phase is a typical example of the 1D PDW state in a superfluid HEM3, and its stability mechanism is attributed to the multiple component of all the parameters. So in that sense, this is the PDW state, essentially different from the PDW state in the superconducting state. So anyway, today I'm going to discuss about the possibility of the formation of 2D PDW state under strong confinement, because our work was originally motivated by recent experimental observation by from the Royal Holloway group, and as Lev already told us, he succeeded in extracting the information of polar distorted order parameter and captured the evidence of the superfluid state, which is composed of unequal amount of the plus domain and minus domain. And this experimental signature can be explained by neither stripe nor translationally invariant PW state. So this suggests the formation of the 2D PDW state under strong confinement. So, but at that moment, no one has clarified the detail of the 2D PDW states. Even the local stability of 2D PDW state has not been clarified at that moment. So our original motivation is to clarify the spatial structure and local and global stability of 2D PDW state. And for this purpose, we utilize the standard GL theory, which gives you a very powerful and tractable tool for understanding the spatially inhomogeneous superfluid state under strong confinement quantitatively. And actually, as you know, the relative stability of various superfluid phases is determined by the bulk fourth order term with 5 beta parameters. And actually, beta parameters are material parameters that contains the information of the quasar particles on in a normal Fermi liquid and contribution from the spin fluctuation and so on. And actually, the beta parameter in superfluid HEM3 has a pressure dependence as well as a temperature dependence. And even at zero pressure, the beta value is significantly deviated from the value of in a weak coupling limit. Namely, the strong coupling correction is not negligible even at zero pressure. Okay, so and the first microscopic calculation of beta parameter was done by Jim Soros and Jocelyn. And recently, the Choi and his collaborator in Northwestern University presented a set of new beta parameters based on analysis of their precise measurement of bulk quantities like a spin susceptibility, like, and so on. And also, Josh Wyman most recently has succeeded in first microscopic calculations that quantitatively reproduce the bulk AB phase transition and critical point along the TC curve. So from now on, I'm going to share with you the numerical result on the PDW state obtained from the GL theory with these two sets of beta parameters. Okay, so let me first make a brief comment on the linear stability of the translationally invariant B phase. Actually, as you know, the bulk, if you consider a bulk system, then the most stable phase is a B phase, which has an isotropic gap. And the order parameter is represented by this diagonal form. But it is well known that this order parameter is very sensitive to the surface condition and the confinement. And actually, let's consider strong confinement along z direction. And then the third component, say AZZ component, is strongly suppressed by the depairing effect at the surface. So this is very sensitive to the surface boundary condition. And actually, in the bulk, the isotropic gap appears in on a film surface, but this isotropic gap is uniaxially distorted by strong confinement. And finally, the B phase undergoes the continuous second order phase transition to the planar or A phase in weak coupling limit. But this is not the end of the story, because usually okay, so this is a phase diagram as a function of temperature and pressure for a particular thickness. And this dotted line is the second order phase transition of the B phase, which is usually covered by the A phase. And so the first order phase transition to the A phase always appears in all pressures. But let's forget the A phase and focus on vicinity of the second order phase transition, because usually the translationally invariant B phase becomes thermodynamically unstable toward the formation of PDW state. And in order to clarify this, we computed the local curvature of the GL free energy around the equilibrium, where we assume the equilibrium state is translationally invariant along the surface. And this estimation of the local curvature can be mapped onto the eigenvalue problems. So if all eigenvalues are positive, then the equilibrium is thermodynamically stable, at least local minimum in GL free energy. But once some of eigenvalues become negative, they are signaling the thermodynamic instability of the translational invariant superfluid phase toward the formation of some PDW state. And let's see what's going on in the B phase. And this is eigenvalues of a fluctuation from the translationally invariant B phase as a function of Q. This is a center of mass momentum of Cooper pairs. And in low temperature, all eigenvalues are positive. So of course, this indicates that the translationally invariant B phase is thermodynamically stable and the local minimum of GL energy. But let's focus on a particular branch here. And this branch shifts downward as temperature increases and touch zero at a finite wave vector in the vicinity of the second order phase transition. And this branch becomes negative as further temperature increases. And these negative values indicates the thermodynamic instability of the translationally invariant B phase toward the formation of the 1dp, formation of the periodic modulation of the superfluid phase. Okay, so for instance, so this is one example of the spatial profile of such a soft mode. Here we take only a single value of the Q vector along the surface, say X direction. And this spatial profile coincides with the well-known spatial profile of the so-called strike phase, because AZZ diagonal component has a periodic modulation along the surface, and each nodal plane can be filled in by induced off-diagonal component. And of course, when you have multiple Q vectors, you have a spatial profile of the two-dimensional PDW state. And this is a story of the thermodynamic instability of translational invariant B phase, which corresponds to the upper bound of the strike phase. And now we move on to the lower bound of the strike phase, which is associated with the nucleation of a single kink and a single dot. So in order to clarify the nucleation mechanism of a single kink and a single dot, we employ the variational calculation. And this is a variational, this is a variational function for the translational invariant BW state. And for simplicity, we assume the spatial uniformity for the XX and the YY component. And the ZZ component is sensitive to the confinement. So we assume the simple form of the spatial profile along the confinement direction like this. And this is similarly, we also assume the variational form for the single kink structure, where the spatial modulation associated with the kink is assumed to this simple hypertangent form. And here, CS is a variational parameter representing the size of the domains. And also, all of diagonal components are variational parameters. So they are, all these variational parameters, of course, are determined by minimizing the free energies. And this is the result. And this is a temperature dependence of the nucleation energy of a single kink. And this clearly shows that the nucleation energy is going to 0 and becomes negative at the critical temperature, which corresponds to the lower bound of the strike phase. And actually, as told before, the upper bound associated with the thermodynamic instability of the translational B phase appears around the temperature 0.85 or 86 or something like that. This is the upper bound of the strike phase. So at least the pressure for this thickness, for this slab with this thickness, the strike phase at least the strike phase becomes metastable in finite temperatures. And another important observation is that this lower bound of the strike phase, I mean a new critical temperature at which nucleation energy becomes 0, is slightly depends on the choice of the beta parameters. And always Josh Wyman's beta parameter theoretical calculation leads to the lower critical temperature than the choice beta. Okay, so now we move on to the nucleation of a single dot. So this is again the nucleation energy of a single isolated dot as a function of a radius, size of a dot. And T star is a critical temperature at which the strike phase becomes thermodynamically stable. So this calculation shows that below the critical temperature, where the spatially uniform B phase is thermodynamically stable, the single dot can be metastable with a finite length, finite radius, which is a scale of the micron or something like that. And also the size of the dot increases as temperature approaches the critical temperatures. And ideally, if you consider an isolated single dot, then the radius of the size of the dot diverges at critical temperature. But in a realistic situation, there is an upper limit, upper bound from the repulsive nature of the interaction between neighboring dots. Actually, this is the interaction energy of neighboring dots, which are separated by the distance L. This is interaction energy below T star, critical temperature. But anyway, this is interaction energy of dot. And this interaction energy is always repulsive and well scaled by L minus squared. So below T star, the neighboring dot shows a repulsive interaction with long range, long range repulsive interactions. And if you take account of the contribution of the dipole interaction energy, then this leads to the attractive interaction between the neighboring dipole, neighboring polka dots, but even below the T star. But I mean, this contribution is approximately fourth order smaller than the main repulsive contribution. So usually this is negligible. So always the polka dot has a long range repulsive interaction. But anyway, as for the nucleation energy, usually nucleation energy is roughly speaking proportional to the length of the domain. Okay, so and the polka dot is in some sense regarded as a vortex ring, and the stripe or single kink is regarded as a vortex. So the length of the vortex is comparable to the size of the system. It's a macroscopic. So we naively expect that a nucleation energy of polka dot is always lower than the nucleation of a single kink. So first, around the T star, polka dots can be nucleated, and this get a crystallization leading to the two-dimensional PDW state above TC, above T star. Okay, so beyond the variational calculation, we employ the full numerical calculation, and this is an example of the spatial profile of 1D PDW and 2D PDW. And the spatial profile of 1D PDW is nothing different from the previous studies. And here is a spatial structure of 2D PDW state in each 9 component. The diagonal component XX and YY has almost uniform constant profile in the unit cell. And the third component, ZZ component, has a sign change from minus to plus. And in the vicinity of the nodal plane, the off-diagonal AZX and AZY can be induced, which plays an important role on stability of the 2D PDW state. And okay, and now I'd like to discuss the strong coupling effect on phase diagram. Actually, upper 2 panels are phase diagram as a function of temperature and pressure for the thickness 0.97 micron and 1.1 micron. Then these phase diagram are obtained from the GL calculation with choice better. And in case of the thickness 1.1 micron, where the lab detected evidence of the spatially modulated phase, in case of the choice beta, there is no stable region of the stripe phase, even at zero pressure. But when we take Wyman's beta, the stripe phase becomes stable in the vicinity of the zero pressure. So, I mean, choice of the beta parameter sensitively changes the phase structure, especially in the high temperature and low pressure region. And the reason is the following. Actually, this is this is a pressure dependence of the strong coupling correction to the beta parameters, say beta 1,2 and beta 2,4,5 and beta 3,4,5 from the choice estimation, and broken curves theoretical calculation by Josh Wyman. And the beta 1,2 and the beta 2,4,5 are quantitatively similar behavior, and there is no big difference between the theory and the experiment. And the big difference appears in 3,4,5, especially in the vicinity of the zero pressure, where the choice beta has a positive correction, but the Wyman's beta brings a negative correction. And actually, this beta 3,4,5 determines the interaction between the order parameter, diagonal component of order parameter, and of diagonal component of order parameter. So beta 3,4,5 may sensitively affect the stability of the induced component around the domain walls. And actually, if you consider hard domain wall, actually the strong coupling correction, strong coupling effect on the hard domain wall have been discussed in this paper. And according to this paper, there is no difference between use of two sets of beta parameters because the hard domain wall cannot induce this off-diagonal component because of the symmetry constraint. But in case of the strike phase, this off-diagonal component plays an important role for the stability of the domain wall, and and this is sensitive to the sign of the beta 345, and that's why the Wyman's beta has a finite stable region of the strike phase at the zero pressure. Okay, so now we discussed the thermodynamic stability of the 2D PDW state compared to the 1D PDW state. And this is a free energy of the 2D PDW state as a function of the temperature, and this is a energy of the strike phase. And this is a zero pressure limit for the slab with a thickness 1.1 micron. And within these parameters, the strike phase is always thermodynamically stable, and the polka dot is metastable. But energy of polka dot is very competitive to the strike phase. Okay, so this is a summary of our observation on the PDW state. The first below the critical temperature where the uniform B phase is thermodynamically stable, the polka dot can be metastable, which behave as a mobile gas with a long-range repulsive interaction. And the size of the gas increases as temperature approaches critical temperatures. And for the higher temperature, the interesting observation is following. The periodic pattern of 2D PDW first showed the brick type texture. But this brick type texture undergoes a kind of a transition to the polka dot structure. And here is a temperature dependence of small q, ratio of the small q and the large q, which is associated with the ratio of the plus and minus domains. And in the brick texture, this q over q value gradually changes from value of the spatially uniform B phase to the 0. And polka dot phase has a small value of the q over q value, which almost stays around the 0.1. This means that the polka dot texture is composed of the almost equal balanced plus and minus domains. And so finally, I want to discuss the experimental measurement compared with our observations. And yeah, if you take of course, the zero pressure limit, our numerical result and the stability of the PDW state is very sensitive to the choice of the beta parameters. And if you take the Wyman's theoretical calculation, then the critical temperature of the strike phase is lower than the A phase critical temperatures. So the strike phase can be thermodynamically stable in a very shallow window, narrow window. And but anyway, in this stable region, the 2D PDW still metastable, but shows a brick-like texture, which gradually, in this brick texture, the q over q value gradually decreases from the unity to 0, which looks like similar behavior observed in the experiment. And of course, the A phase appears. So usually polka dot texture cannot be observed in this parameter region. But if you consider a polka dot structure, we found that this polka dot may be unstable toward a one-dimensional stripe order. So in a previous slide, we observed a stable polka dot structure in high temperature region, but in this calculation, we impose a triangular lattice symmetry. So we, in some sense, we force the polka dot to be stabilized by a symmetry constraint. But if we remove such a symmetry constraint, the polka dot structure texture becomes unstable toward a 1D stripe order. But the brick can be metastable. So, okay, so this is my conclusion. We computed the nucleation energy of a single dot, which is lower than that of the nucleation, that of a single domain wall. So we hopefully, we expect that first polka dot can be nucleated in the vicinity of the critical temperature, which get the crystallization above TC, leading to the two-dimensional PDW structure. And actually, the thermodynamic stability of PDW is very sensitive to the choice of the beta parameters, at least at zero pressure and high temperature regions. And 2D PDW, especially polka dot texture, is not always a local minimum of GL energy and unstable toward the formation of the one-dimensional PDW state. So that's all. Thank you for your attention.
Thank you very much for a very interesting presentation. Do we have any questions from the audience?
I do.
Go ahead.
Takeshi, very nice presentation. I just had one question about how did you isolate the so-called dot-dot interaction? Did you consider only two dots? And
yes, we assumed the variational function for two dots separated by finite distance in a single unit cell.
mm-hmm.
And size of a unit cell is sufficiently large compared to the distance of the single dot.